Ladies and gentlemen, in your reading on intermolecular forces, we had a lovely section there which talked about polar, and I said to you that I'd be giving you something to help you understand that. So let's have a look at this thing which we call a polar bond or a polar molecule. Now, when we're doing this, the whole principle, in the other video we saw that electrons are the key. Polar bonds we're going to talk about are the covalent type, the ones that form between non-metals. So they exist sometimes, and we're going to look at one at the end. Review. When we started looking at covalent bonds, which was a really quick introduction at the end of our last lesson, one of these, we saw that the overlap of the electrons allows them to be shared between this and this. Now, if they're the same thing like hydrogen or oxygen or nitrogen, then there'll be this even sharing, and we'll have some lovely symmetry. And that simply means that the molecule, here we have two atoms making together form a molecule, will be the same on both sides. Now, scientists can actually study if the electrons are spread evenly around inside a molecule. They can actually do that. They look at what we call an electron density map. But we'll see one of those in a minute. But I like this. We've got this same thing going through. The symmetry, equal sharing, electrons spend equal time near each nucleus, so we have a non-polar bond. So it's only when we upset the apple cart and we have one of the atoms stronger than the other, or have a stronger pull on the electrons, then we have a problem. So if we have an uneven sharing, like over here we've got two examples. We've got the same atom, so if they're the same atom, one would hope they're equal. And if they're equal, we'd have symmetry and we'd have non-polar. But if they're different atoms, sometimes one is much more than stronger and has a much higher attraction to the electrons than the other. Now, if we look at this one, this is what I'd call an electron density map. Here we've gone from a beautiful symmetrical thing. Now we've got it narrow at this end and wider at this end. So this tells me that the electrons spend more time here than they do here. And so we get what's called a partial difference in there. Right? We get a partial difference or an uneven sharing, and it's almost like we have an artificial, one end of it becomes more electron heavy, or the electron spends more time there. So we say it's got a negative bit, a little bit negative. And if it's got less time here, then we just compare it. So we say it's, well, compared to the other end, this one's a little bit positive. Now, if you've created two ends that aren't the same, in there, if they're the same atom, then the ends are identical. So we have the symmetry. So there will be no opposite ends. There's no such thing as an opposite end in this one. But when we have something like the HF that we saw on the last slide, then what actually happens is we have one thing that looks like a different to the other end. We have differences. And so we use the term poles or polar to talk about this. Now think about it when you learn about magnets. You've got magnetic field around a magnet, little bar magnet. We had the N north end and the S south end. If we think about it, it's also the same as the Earth. We've got a south pole and a north pole. So if we've got two different ends to a molecule, then we have a polar molecule. That sounds easy, doesn't it? Now let's have a look at which one is really super important to us and all living things. Water has got 1, 2 hydrogens and 1 oxygen. And we actually find out that the electrons spend much more time at the oxygen side than they do at the hydrogen side. So this has got a little bit, because the electrons are there more often, this would have a little bit negative side, and the hydrogen compared to it has a little bit positive side. So hydrogen has polar bonds, uneven sharing of electrons in the bonds, and the whole molecule is polar. Now this is really lucky for us, because what it does is it allows the water molecule to be attracted to nearby water molecules, and they set up a special bond between them. Now this is an intermolecular bond, and it's called a hydrogen bond, and it joins, if you like, a whole series of water molecules together. And this explains why we hurt ourselves when we don't get our dive right off the diving board, because the hydrogen bonds in the water make the skin of the water, the surface tension of the water, a bit stronger, and we have to burst through that when we dive into the water. So that's the part that hurts. But the best part is that because it does this, it has changed the boiling point of water. Without hydrogen bonds, water would boil at about -100 C. But we know that water actually boils at 100 C. So these intermolecular forces between the water molecules are strong enough to raise the boiling point by a lot. And we find this is a really constant pattern between any of the molecules that are polar. When they are together, their boiling point is much higher. I'm going to leave it at that and hope